You build an agent. It answers questions perfectly in staging. Then real users hit the endpoint, and the entire architecture shatters under production load. McKinsey and Generation RAG identify the primary drivers of these failures as retrieval quality issues, governance gaps, and the failure to treat RAG as a living system that requires ongoing attention. When an agent fails in production, the standard engineering instinct is to debug the prompt or swap the underlying LLM. The data shows this is almost always the wrong move. I'm Bearded AI Guy. Today, we map the architecture required to survive production. We will build the 5x5 mechanism grid, calibrate the distinct thresholds for B2B versus B2C deployments, and locate the exact automation sweet spot for 2026. Agent failure is rarely a model problem. It is a systems architecture problem, driven almost entirely by engineers confusing two very different operational requirements. The first requirement is grounding. This is the discipline of forcing the agent to explicitly prove its work. Every factual claim must be tethered to a retrieved document or a customer record. When grounding fails, the model hallucinates. It invents plausible, highly confident information that is simply false. The second requirement is guardrails. These are the physical fences placed around the agent's capabilities, strictly dictating what tasks it is authorized to execute. This split pipeline shows the divergence. Grounding handles the data. Guardrails handle the actions. When guardrails fail, the agent executes unsafe tasks, like promising a refund to a user who doesn't qualify, or leaking personally identifiable information into the chat window. You can have an agent that quotes your knowledge base perfectly, but actively processes refunds it has no authority to make. Or you can have an agent that stays strictly within its permitted scope, while hallucinating product features that do not exist. Grounding keeps the model honest. Guardrails keep the model safe. Treat them as the same problem, misallocate your engineering resources, and the deployment will fail. A grounding filter operates by stripping away the model's parametric memory. It forces the LLM to ignore what it learned during pre-training and rely exclusively on the specific text chunks you feed it. Enforcing that restriction in a live environment requires a specific layered stack of mechanisms. This stack outlines the 5 layers. Layer 1 is retrieval-conditioned generation, establishing a prompt-level floor. Layer 2 applies Anthropic's Citations API for exact source attribution. In early 2025, Endex applied this API and reduced source hallucinations and formatting issues from 10% to 0. Layer 3 is self-verification. We insert a fast LLM-as-a-judge, like Haiku, to evaluate the response against the context. Layer 4 forces that output into rigid JSON schemas. OpenAI reports a failure rate below 0.1% across 500,000 calls using structured outputs. Layer 5 is refusal training, explicitly instructing the model to reply, "I do not know," when the retrieved evidence is insufficient. The default 2026 starting stack combines retrieval constraints, the Citations API, and refusal training. Relying on a single mechanism leaves vulnerabilities. When composed together, they create a constrained environment where the model cannot successfully lie. Guardrails operate differently. They are structural roadblocks. They physically intercept the agent and block specific actions, regardless of the instructions a user types into the prompt. Similar to grounding, effective safety requires layering multiple technical constraints. Here is the guardrail stack. Mechanism 1 establishes anti-goals in the prompt, cheap but easily bypassed. Mechanism 2 is strict limitation of the tool surface itself. If the delete account function is not passed to the model, the agent mechanically cannot delete an account. Mechanism 3 implements output filtering hooks. By tying logic to the post-tool use and stop events, you intercept the data and block severe violations before the payload ever leaves your server. Mechanism 4 integrates dedicated policy classifiers. Small models, like the 86 million parameter Llama Prompt Guard 2, catch injection attempts in 20 to 50 milliseconds. Mechanism 5 wraps these classifiers inside overarching orchestration frameworks, like Meta's Llama Firewall. True safety is not achieved by instructing the model to behave nicely. It is achieved by removing its mechanical ability to misbehave. An anonymous user attempting to jailbreak a B2C application on the open web presents a very specific threat. An authenticated B2B customer, bound by a master services agreement and managed by a success team, presents a completely different one. The asymmetry of error matters. The code for the guardrails might be identical, but the thresholds must be calibrated to the environment. If you apply aggressive, open web B2C guardrails to a closed B2B platform, you generate catastrophic false positives. You block legitimate queries. You frustrate paying customers. And you flood your human support engineers with unnecessary escalations. This slider illustrates the automation trade-off. If your safety rules are too tight, you hit 30 to 40% automation, which makes the system unprofitable. If your rules are too loose, you hit 90% automation, but the quality variance across those conversations is completely unacceptable. The indicator settles in the green zone. For B2B RAG agents in 2026, the operational sweet spot sits squarely between 65 and 75% automation. Pushing for maximum automation is a dangerous vanity metric. The actual engineering objective is tuning the thresholds to block malice without punishing your customers. Securing your system does not require rebuilding the base agent from scratch. You slide interception nets directly onto the agent's output channel. You implement this by binding standard SDK hooks to the events in your application code. Look at this Claude Agent options configuration. When the agent attempts to stop, 3 hooks fire in sequence. 1. Check grounding. This haiku call identifies grounding drift, where the model's accuracy begins to slip as your underlying knowledge base evolves or retrieval quality fluctuates. The remaining hooks redact PII and moderate the output. Each hook either returns a clean pass or flags an action block. If blocked, the agent is forced to re-retrieve its context or escalate the ticket directly to a human. Running this composed stack at scale, processing 50,000 conversations a month, adds roughly $20 to $50 in total compute costs. That API cost is a statistical rounding error compared to the financial damage of a single hallucinated contract term or unauthorized refund. Grounding prevents invention, guardrails prevent action, and your specific business context dictates exactly how you tune the thresholds between them. As Anthropic explicitly points out, eliminating hallucinations entirely is a mathematical impossibility for large language models. This grid contrasts the two states. On the left, an unmonitored agent silently leaks PII to the user. On the right, the exact same leak occurs, but SDK hooks intercept it. The payload is blocked, flagged, and logged before the user sees it. The objective of this architecture is to ensure that when the model inevitably hallucinates, the error is immediately detectable, attributable to a specific step, and recoverable. A production-ready stack ensures that every failure mode is detectable, attributable, and recoverable. Take a hard look at your own logs. Drop a comment below with the specific failure mode you suspect is currently invisible in your stack. Tomorrow is day 6, observability and stack traces. The interception hooks we built today are useless if their signals aren't being indexed and queried. Grounding drift, the slow decay of accuracy as your data evolves, shows up in CSAT long before it triggers an engineering alert. I'm Bearded AI Guy. See you tomorrow.